This video lecture is about box models, and box models are a tool to describe how the concentration of any given element or constituent in the ocean varies as a function of its input and output processes in the ocean as a whole. So if we think about the ocean as a box, and we consider that there are inputs of various elements or constituents, and that there's also outputs, we can use this simple formulation to describe the concentrations of elements in the ocean. If we define a few variables here, V is the volume of the ocean. And if we say that Ci is the concentration of element I, then we can essentially write an equation write some equations to describe what's going on here. So the product of V and C, V times Ci, is equal to the inventory of that element in the ocean. So what that means is that that's how much there is. So for the concentration is in maybe moles per cubic meter, and the volume is in cubic meters. And so those cubic meters cancel out, and so we get moles. So that's the number of moles of constituent I that are found in the ocean. And so we can also think about what defines these inputs and outputs. We can make some basic assumptions regarding them. So inputs, if we consider that the primary input for a lot of constituents in the oceans comes from the rivers, we can write the input of constituent I is equal to the volumetric flow rate of the river, of all the rivers coming into the ocean, times whatever concentration of constituent I is in the rivers, is in the river water. So if the concentration of an element is high in the river water, then that means there's a lot of inputs of that constituent into the oceans. Similarly, if the volumetric flow rate of the rivers were to increase, say because of an increase in precipitation or melting glaciers, then this would cause an increase in that. And so those are the two main parameters that cause that control the input of a constituent into the ocean. Similarly, we might consider outputs, and we can model the outputs in many cases as proportional to the concentration of the element in the ocean itself. So the loss is equal to, for example, K times Ci times V. And so this is essentially K is a proportional loss rate, and this can be in units of years per year, sorry. And then we know, of course, that C is in moles per meter cubed, and V is in, again, meters cubed, cubic meters. And so if we get this comes out to be moles per year. And And similarly for the inputs, if the volumetric flow rate is a cubic meters per year and the concentration is in moles per cubic meter, this is also in moles per year. So what we can do then is we can think about our third hypothesis, which is that the ocean concentrations are controlled by kinetics, and it's the balance between these inputs and outputs that determine the concentrations. And as such, since the concentrations of many elements are stable over long periods of time and have been, that means that the inputs are essentially equal to the outputs. And so that's our steady state assumption. So steady state means inputs equals outputs. So in other words, this term is going to equal that one. So if we write that out, that means the volumetric flow rate of the river times the concentrations of the river is equal to K I C I times V. Rearranging this equation, we get CI equals V river times C river over the rate constant K and times V. So, and again, this comes from this equivalency here, and this model comes from the fact that if we assume that at steady state, the change in the inventory, or V times CI is zero over time is zero, then the inputs are equal to the losses. Finally, a few quick definitions here that we can use to discuss this. We can define a residence time. And we can call that tau. And tau is essentially equal to 1 over k, and it's in years. And it's essentially the average time that a chemical or constituent spends in the ocean before it is removed. So how long on average does calcium, for example, stay in the ocean before it's removed? That is reported in residence time, and it's a function of the years. So if K is small, then tau is large, and the ocean concentration is high. And that means that's because essentially anything that comes into the ocean stays there for a long time and just accumulates there. So given the definition of residence time, we can rewrite this equation here and describe it as tau times V river times C river over V. And oftentimes we're interested in what that residence time is, and so we can rearrange this equation and come up with a value for tau based on the parameters that we know, like the river flow rates and concentrations in the river and the volumetric in the ocean. And that comes out to be CI times V ocean over V river, flow rate of the river times the concentration of the river. And so this is a fairly useful term, and we'll be using this in some of the practice problems in the rest of the class.